Good evening, chemistry curmudgeons. We're going to be doing a screencast for the first topic in Unit 5 on chemical nomenclature, and I'm specifically going to be dealing with the examples where I give you the formula and I want you to supply me with the chemical name. So first I'm going to introduce you to our most massive flowchart of the year and walk through how to use it along with some examples. So here is our massively huge, wonderful flowchart. I'll zoom out here so you can see it in all of its glory. I see one thing here didn't survive the conversion to PDF very well. Hopefully we can work with that. So we've got one question here. The very first question is asking us, are there more than two elements? And that starts us off. We're going to be doing the no branch first because it's kind of shorter, and then come back to the very top and do the yes branch. So let's dig into it and look at some examples. So our first question is going to be asking, are there more than two elements? And this is a good first question because everything in this class that has more than two elements definitely will have a polyatomic ion in it, and you'll need to get out your polyatomic ion list to identify which that is. If there are not more than two elements, you may still have a polyatomic ion, or you may not. If it's a polyatomic ion, it's going to be one of these four. That should be an azide, N3 with a -3 charge. Sorry about that. It will be one of these four. And this doesn't get called out with the first question because each of these four only has one kind of element in it. So you have to be very careful if you've got one of those. And the first thing that I'm going to look at is actually an example of how to spot one of these, and you have to be familiar with what their charge is to see if you can figure these out. So let's take this over here to the side for a moment and consider these two examples, CO2 and CaO2. On first glance, you might think that these still have a polyatomic ion because here you have the peroxide ion, which is O2 with a -2 charge, and both of these have O2 in them. However, it might also be the case that there just happen to be two oxygen ions, not as the polyatomic ion. So let's consider each of those for these two examples. If we have carbon and a peroxide, and the peroxide is a -2, that's going to mean that carbon is +2. Or if we have carbon with two oxygen ions, they're each -2. You should remember that this is the charge based on their location on the periodic table. Their most common charge would become isoelectric with the noble gas. Because we've got two things that are -2, that means our carbon would be +4. And you have to look at the charge of the positive species to decide for carbon which is more logical, a +2 charge or +4 charge. Hopefully at this point in the year you can say that carbon is going to have a +2 charge, and it's not carbon with a +2. So this means we still do not have a polyatomic ion, that this is just carbon with two oxygen ions. Okay, let's look at my second example here. Again, we could have calcium with the peroxide being -2, so calcium would be +2. Or we could have calcium with two oxygen ions, each one -2, which would make this +4. Now everything that you know about calcium at this point in the year should tell you that this is the correct choice, not this. So in this case, you do have a polyatomic ion. So this is probably one of the trickiest questions here in this in this flowchart, and you have to be aware of what the charge of the polyatomic ions are, as well as what the common charge for oxygen, nitrogen, or sulfur. Dimercury doesn't really apply because it's a cation. We'll mainly be looking at anions, so you have to be aware of what the charge of oxygen ion, nitrogen ion, and sulfur ion is, and be able to compare that with the charge of the polyatomic ion to see which gives you a logical choice for the charge of the cation. So this can be very, very tough, but we'll look at some more examples with it in class. Okay, let me get rid of all of these so that we can go back to the flowchart. Alright, wonderful. So we're going to say, in this case, no, we do not have a polyatomic ion. So at this point we know that we have some kind of a binary compound, which just means that we're composed of two kinds of elements without a polyatomic ion. The first thing that I want you to look at now is, does it begin with an H? If it begins with an H, you're going to have some kind of mineral acid. And our rule for mineral acids is to say the prefix hydro, take the element and convert its ending to ic, and add acid. For instance, if we had HCl, this is going to get converted into hydrochloric acid. Take the prefix hydro, chlorine, convert its ending to ic, so chloric, and add acid. So store this hydrochloric acid in your goldfish brains for when we talk about acids on the other side of the periodic table, other side of the flowchart. Okay, if it does not begin with an H, now you need to ask yourself, what kind of element is the element with the lower electronegativity? By the way, this is an important thing to remember to save you time. Chemists always list the element with the lower electronegativity first. If the thing with the lower electronegativity is a nonmetal, we have a binary covalent molecule, and we're going to be using numeric prefixes. And we're going to switch the second element, the more electronegative element, its ending to "ide." So if we had P4O10, this is going to turn into tetraphosphorus, because there are 4 dec oxide, because there are 10. Okay. Now what if it is a metal instead of a nonmetal? Well, we have a couple of rules off of this, and it all depends on whether it's a metal where you can be sure of its charge. Aluminum is always going to be +3, and the elements in the S block are always going to be +1 or +2, depending on whether they're the first group or the second group. So if we do fall in one of these situations, we're confident of the charge, and we have a simpler rule. NaCl. Na is in the first group of the S block, so this rule is just going to be sodium, and we're going to be converting the anion, the chlorine, to chloride. And that is that. Unfortunately, though, if your element falls outside of aluminum or the S block, you're not going to be certain on what the charge is, so you're going to have to do some work. However, in this class you will always know what the charge of the anion is, either because it's a member of one of the group 15, 16, or 17 on the periodic table, where they'll be -3, -2, or -1 respectively, or it's going to be a polyatomic ion, and that list will tell you the charge. So what I'm getting at is you will always know the charge of the negative species and be able to use that to figure out the charge of the positive species. And then once you find that charge, you're going to put it in Roman numerals and switch your anion to "ide." Now I'm going to zoom down here to the bottom. There's that mess up. Hopefully after some practice this just sort of becomes mental math, but this is what I'm going to be doing to figure out the charge of the cation. I'm going to use the charge of the anion multiplied by the number of anions divided by the charge of the number of the cations, and that will let me figure out the charge of the cation. So let's do an example using that rule. So let's say we have some rust, Fe2O3. Iron is right in the middle of the D block, so it's definitely not a member of the S block or aluminum, so we're going to be uncertain of its charge. Oxygen, however, it's in group 16, so you should know that it is a -2. So I'm going to say 3 oxygens times, I'm just going to use the absolute value of this because we're solving for the positive cation, times 2, because oxygen is -2, divided by my number of ions, which is 2. So this tells me that I have iron plus 3. So I'm going to write this: iron, Roman numeral 3, oxygen, ending switch to "ide," oxide. Okay, there ends this side of the flowchart. Now we can go all the way back up to the top and run us into there are 2 ways to get to the situation where you have a polyatomic ion. Either you have more than 2 elements, so 3 or more elements, that's going to send you here, or you've got one of these 4 really annoying things, and we talked about how to identify those using the charge. So either case, you're over here, and you now need to, whether you've memorized it or you found it off the list, you need to identify the polyatomic ion. Now just like we had H's make an acid on the other side, H's added to the polyatomic ions will make them into an acid also. I'm trying to be careful here to say additional H's so that you're not confused by something like this polyatomic ion, which is, this is acetate. So I'm not talking about does the polyatomic ion have H's in it. I'm talking about has acetate been bonded to additional H's besides what's in it. So be careful with that. So let's say that we have a polyatomic ion and it does have H's added to it. It is now what we refer to as an oxyacid. And you're going to look at whether the polyatomic ion ends in -ite or -ate. So I'm going to use 2 similarly named polyatomic ions for my examples. Alright, so in each of these examples I have 3 elements, hydrogen, chlorine, and oxygen. So there are more than 2 elements. And we've identified the polyatomic ions. This one is chlorite, and this one is chlorate. ClO2 is chlorite, ClO3 is chlorate. So the ite rule tells us that chlorite is going to have its ending switch to chlorus. So this is chlorous acid. And the 8 rule is going to tell us that the 8 gets its ending switched to chloric acid. Now you remember a few minutes ago I asked you to store hydrochloric acid in your goldfish brains. This does not have the hydro prefix, so you definitely need to be able to tell HCl apart from HClO3. And you would want to do that as a chemist, because if you had to dunk your hand in one of these, you should choose the chloric acid. Much, much, much less harmful than the hydrochloric acid. So, all in the name, one little prefix is the difference between a relatively weak acid versus some really, really potent stuff. So, let's knock these out, and we will go back up to, is the polyatomic ion bonded to H's? We're going to say no. Now you need to make a quick check to make sure that both components, the cation and the anion, aren't both polyatomic ions. If they are, then you're going to come here. And this is a really easy rule, because all you do is name both of the polyatomic ions. So for instance, if you had we have more than 2 elements. We have N, H, and O. We've not bonded additional H's because this is the polyatomic ion ammonium. So no additional H's have been bonded to ammonium. And this is the polyatomic ion nitrate. So both the cation and the anion are made of polyatomic ions. So this one's name is simply going to be ammonium nitrate, common fertilizer ingredient. Go away. Go away. Okay. Now let's say, is it made of 2 polyatomic ions? No. We're going to come down and we have similar questions as before about what is the cation, where if you've got the ones that aren't in the S block, I'm sorry, you're going to hate those. We'll save that for last. Let's say your cation is a metal and it is a member of aluminum or the S block. And our example here is, okay, more than 2 elements. Yes, sodium, oxygen, and hydrogen. Identify the polyatomic ion is hydroxide. So that is OH minus. We've not bonded additional hydrogens to our polyatomic ion, so this isn't one of the oxyacids. Both parts aren't polyatomic ions, and sodium is in the first group. So this one is sodium hydroxide. Don't need to indicate a charge because the common charge on sodium is +1. Okay, now let's look at the part of my rule here that kind of got garbled off. The cation could be one of the polyatomic ions. There are a handful that are cations, not that many. It's far more common for the polyatomic ions to be anions, but anyway, could be here. So you could have something like this, where we talked about this before. The NH4 is ammonium, and this is NH4 plus with Cl minus. So our cation, the positive part, is our polyatomic ion. So now we're just going to name the polyatomic ion, and then as before switch our anions ending to -ide. So ammonium chloride. I've been on a theme with chlorine for this screencast. Okay, and our last rule, oops, I thought I grabbed all of you guys, guess I didn't. And our last rule is that nasty rule where you've got something in the D block or other metals where you're uncertain of what the charge on the cation is going to be, and you have to use the charge of the anion to figure out what it is. Let's say we have something, oh, I don't know, let's be obnoxious here. It's not what I wanted. One tidbit, whenever you see parentheses, that means more than one polyatomic ion. Whatever is in parentheses is a dead giveaway. That's what your polyatomic ion is. So here our polyatomic ion is phosphate. And phosphate is a -3. So I have 7 things with a charge of 3 divided by 3 rutheniums, and so that means ruthenium is +7. So I'm going to name this compound ruthenium 7 phosphate. Okay, we're going to end up with a couple of grammar issues. There's a few more on the next slide. One of them I actually want to handle while we're looking at this polyatomic ion, and that is sometimes students getting confused about this rule. So you will see things like carbonate, and you'll see bicarbonate, and then you'll see this. These two are listed on your polyatomic ion, carbonate and hydrogen carbonate or bicarbonate, either or. And then this is the acid. Carbon 8, so I'm converting the 8 ending to ic. This is carbonic acid. Okay. Some students might get confused and want to call this carbonic acid also, because it is a hydrogen added to a carbonate. This is not yet a neutral species, so it will need some other element added to it. I wanted to erase that, just that X. I guess it's not going to allow me to, so remember that charge now. So this is not like sodium carbonic acid. This is sodium bicarbonate. So yes, I realize that this is a polyatomic ion with an additional H to it. That is still not quite yet a neutral species because this is a -2. So to get the acid, you need to add 2 hydrogens to it. In a similar vein, but even more complicated, you have phosphates. I guess I'm going to be writing in, I don't want to write red. I don't want to talk about phosphites. I want to talk about phosphates. Phosphate, hydrogen phosphate. If you're with me now, you'll see that that is going to be a -2 because we've added 1 hydrogen to it. Dihydrogen phosphate, -1 because now we've added 2. And this is the only one that you should be calling an acid, because the original polyatomic ion was a -3, so to get the acid you have to add 3 to it. So this is phosphoric acid. All of these are going to have other cations added to them. So if I added 2 sodiums, I would have to have 2 sodiums to cancel this out, 1 sodium to cancel this out, 3 sodiums to cancel this out. So be careful with some of these polyatomic ions that have charges more than -1, because you could have partially hydrogenated polyatomic ions where you've added only 1 or 2 hydrogens but not enough to completely cancel the charge. Those are not acids. Only the one that is just the polyatomic ion with only hydrogens are the acids. Whew! Let's look at 2 other grammar things and we will be done. Okay. When you get to the one rule on the flowchart where you use the numeric prefixes, let's talk about using the prefix mono. This is properly carbon monoxide, not monocarbon monoxide. For some reason, it was decided some time ago that when you're using the prefixes, if the first element is mono, you leave its prefix off. You only will use mono to describe the second element. So remember that. If you see this, yes, I realize that there's 1 carbon, and it's falling under the category where you use the numeric prefixes, but mono will never be used for the first element, only if the second one is mono. And you saw there in the flowchart that you will often be making endings of elements, converting them to "ide," "ik," or "us." These 2 elements, phosphorus and sulfur, are inconsistent about where they apply that ending to in the original element. So it's phosphide, so you're chopping it off after the pH and converting to it, but it isn't phosphic or phosphorus. Phosphoric, so you're cutting it only the US off of the phosphorus, and same here, you're only cutting off the US, so be careful on that. Same for sulfur. Sulfide, but not sulfic and sulfus. Sulfuric and sulfurous. All of your other elements are more consistent. So if we picked, I don't know, nitrogen, it's going to be nitride, nitric, nitrous. So all your other elements are at least consistent about where in the element's original name that they cut it off and make the conversion. But watch out for phosphorus and sulfur. So anyway, some little things. Hopefully this avoids some common mistakes on your practice set, and we will do another video where we go the other direction. I give you names, you give me formulas. Until next time, memorize those polyatomic ions.